NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new.
NASA says it just found a new planet.
Shocking, right? Yeah, the James Webb Telescope spotted it just outside of our solar system.
What if the very foundation of modern cosmology was shaken to its core? Not in a matter of centuries or decades, but years. Well, that's what's happening. Well, the James Webb Telescope has just detected a terrifying object in space. Experts now worry that the standard Lambda Cold Dark Matter model, which predicts a slower, more gradual evolution of structure in the early universe, may have been wrong all along. Today, we'll unveil the whole truth, redefining our understanding of the early universe. Launched by NASA on December 25, 2021, and stationed at the Sun-Earth L2 Lagrange point, the James Webb Space Telescope, or JWST, has begun to deliver observations that are upending our fundamental understanding of the cosmos. In 2023, data from JWST's Near-Infrared Camera, or NIRCam, revealed the existence of 6 candidate galaxies at redshifts greater than 7, meaning that their light has traveled over 13 billion years to reach us, placing their origin just 500 to 700 million years after the Big Bang. These galaxies, observed in the Cosmic Evolution Early Release Science, or SEERS survey, stunned the astrophysical community. What made these galaxies particularly controversial was their estimated mass, which is comparable to, or even exceeding, that of the Milky Way, which contains about 100 to 200 billion stars and has had over 13 billion years to accumulate that mass. Just imagine the ramifications. All our estimates about the history of the universe have been falsified in just 2 years. One of these galaxies, labeled SEERS 1749, was estimated to have a stellar mass of approximately 100 billion solar masses, yet appear to have formed within 700 million years of the universe's birth. Another, SEERS 9336, displayed similar properties, challenging the accepted timeline for hierarchical galaxy formation. According to the Lambda Cold Dark Matter model, the prevailing cosmological framework, structures of this size and complexity should not have had enough time to assemble so early in cosmic history. Galaxies were expected to begin as small, irregular clumps of matter, gradually merging over billions of years to form the large spiral and elliptical systems we see today. These findings were initially met with skepticism, in part because estimating stellar masses and redshifts at such early epochs is fraught with uncertainties. Redshift is a measure of how much a galaxy's light has been stretched due to the universe's expansion, and can be miscalculated if not properly confirmed via spectroscopic methods. Nonetheless, follow-up observations using JWST's Near-Infrared Spectrograph, or NIR-SPEC, began to confirm the high redshift nature of these galaxies. If galaxies of such mass and maturity really did exist this early, then either the universe formed stars much more efficiently in its early stages than previously thought, or some unknown process accelerated galaxy growth. One possibility is that dark matter, which provides the gravitational scaffolding for galaxy formation, may behave differently at small scales or during early cosmic epochs than current models suggest. Alternatively, the processes governing star formation might be more dynamic and efficient under extreme early universe conditions than previously assumed. Another hypothesis gaining attention involves modifications to the theory of cosmic inflation, or the rapid expansion of the universe fractions of a second after the Big Bang. Some theorists propose that inflation may have left behind regions of enhanced density that seeded the accelerated growth of certain structures. Others believe that we may be missing an important piece in our understanding of the early universe: the powerful influence of early supermassive black holes, or extremely energetic explosions known as hypernovae. These objects release enormous amounts of energy, and that energy could have jump-started the process of star formation much faster than we expected. Instead of stars and galaxies slowly taking shape over hundreds of millions of years, these intense feedback mechanisms, like radiation, shockwaves, and heat, might have created pockets in the early universe where gas collapsed quickly to form stars and galaxies. Certain areas of space may have gotten an early boost, or kickstart from these cosmic giants, helping them grow up faster than the rest of the universe. But wait, we're not done with paradigm-shifting stuff just yet. Impossible structures and missing ingredients. According to well-established astrophysical theory, the universe after the Big Bang consisted almost entirely of hydrogen and helium, with virtually no heavier elements, known collectively as metals in astronomical terms. These metals form inside stars and are released into space when stars explode as supernovae. So when JWST detects elements like carbon, oxygen, and iron in galaxies that formed just a few 100 million years after the Big Bang, it presents a serious puzzle. How did these materials get there so quickly? This issue came into sharp focus in 2023 during data analysis from the JADES, or JWST, Advanced Deep Extragalactic Survey Program, which focused on a patch of sky near the constellation Fornax. The program identified several galaxies at redshifts greater than 10, meaning the light we see from them was emitted more than 13.2 billion years ago. One standout example, a galaxy known as JADES GS Z130, appears to have formed a mere 320 million years after the Big Bang. Yet even at that early stage, its spectrum revealed the presence of oxygen. This element should not have existed in significant quantities unless at least one generation of stars had already lived and died. In standard cosmology, the first stars, known as population 3 stars, were massive, hot, and short-lived, composed almost entirely of hydrogen and helium. These stars are thought to have ended their lives in powerful supernova explosions, enriching their surroundings with the first heavy elements. However, such a process, followed by the collapse of this enriched gas into new stars and galaxies, known as population 2 and later population 1 stars, should have taken more time than these early galaxies appear to have had. The existence of heavy elements in galaxies less than 500 million years old suggests that either star formation began much earlier than we thought, or it occurred far more rapidly and efficiently. One key example of this conundrum is GNZ11, a galaxy initially observed by the Hubble Space Telescope and further studied by JWST. Situated at a redshift of about 10.6, GNZ11's light has been traveling for about 13.4 billion years. Observations using JWST's near-infrared spectrograph, or NIR spec, revealed not only ultraviolet emission lines indicative of young hot stars, but also spectral signatures of elements like carbon and silicon. These findings imply that at least one generation of massive stars had already exploded as supernovae, seeding the galaxy with heavier elements. All of this within a cosmic blink of an eye after the universe's birth. This rapid chemical evolution is also inferred from the presence of dust in these early galaxies. Cosmic dust, composed of tiny grains of silicates, carbon, and iron, forms in the outer atmospheres of aging stars and the remnants of supernovae. For dust to be present at such early epochs means that not only had stars formed and died, but their material had already begun cycling through the interstellar medium. JWST's MIRI, or mid-infrared instrument, confirmed the infrared signatures of dust in several galaxies at redshifts above 7, such as MAX 0647JD, lending further support to the idea that the early universe was chemically complex much sooner than expected. The implications of these discoveries ripple through multiple areas of astrophysics. For one, they challenge current assumptions about the timeline and nature of population 3 stars. While these first stars have never been directly observed, their characteristics are modeled based on the conditions of the primordial universe. They are assumed to have been 100 to 300 times more massive than the Sun and to have lived just a few million years. If JWST's findings are accurate, it could mean that population 3 stars formed and died earlier and more prolifically than previously modeled. Moreover, the observed maturity of these early galaxies might suggest the existence of processes we don't yet fully understand, either unknown pathways for heavy element production or mechanisms that drastically enhance the rate of star formation and evolution. One possibility is that early galaxy environments were more conducive to rapid star birth, perhaps due to denser pockets of gas or different dynamics in the cosmic web. Alternatively, exotic processes such as primordial black holes or interactions involving dark matter could have played a catalytic role in early star and galaxy formation, though these ideas remain speculative. Another challenge lies in reconciling these findings with computer simulations of cosmic evolution, such as the Illustris TNG and Eagle projects. These large-scale simulations attempt to model the formation of galaxies over billions of years, incorporating dark matter physics, gas dynamics, star formation, and feedback from supernova and black holes. But JWST's data indicates that these simulations may need to be recalibrated or expanded. In parallel, astrophysicists are working to confirm the JWST findings using spectroscopic redshift measurements, which offer more precise distance estimates than photometric redshifts. In 2024, preliminary results from the JWST Spectroscopic Survey, or JSS, began confirming the redshift and chemical compositions of several early galaxies previously identified as outliers. These confirmations are bolstering the case that JWST is not merely observing statistical anomalies, but instead uncovering a consistent pattern that demands theoretical reinterpretation. As JWST continues its mission, it will uncover even more examples of these impossible structures, prompting a re-evaluation of everything from the first stars to the processes that built the periodic table. What was once a smooth, orderly picture of cosmic evolution now appears more chaotic, dynamic, and surprising than ever before. Speaking of surprises, what about those unusual exoplanets? Among the most striking contributions of the JWST has been the detailed study of exoplanet atmospheres, especially those of hot Jupiters and other unusual planets that defy existing models. These exoplanets are gas giants that orbit extremely close to their stars, often completing an orbit in just a few Earth days. Their scorching temperatures often exceed 1000 degrees Celsius. Imagine that. One of the most attention-grabbing discoveries came from observations of WSP-39b, a Saturn-mass exoplanet located 700 light-years away in the constellation Virgo. Observed during JWST's Early Release Science or ERS program in mid-2022, WSP-39b orbits its host star once every 4 Earth days and has an atmospheric temperature of around 900 degrees Celsius. JWST's spectroscopic data revealed the unmistakable presence of sulfur dioxide in its atmosphere, an unexpected molecule because it forms only through photochemical reactions, which occur when ultraviolet radiation from the host star interacts with atmospheric molecules. This marked the first direct detection of photochemistry on an exoplanet. In addition to sulfur dioxide, JWST also found carbon dioxide, water vapor, and carbon monoxide in the same atmosphere, allowing scientists to create the most complete atmospheric profile of any exoplanet to date. More puzzling was the detection of significant chemical disequilibrium, meaning that the atmospheric composition did not match what models would predict for a planet in thermodynamic balance. Such disequilibrium suggests that unknown chemical reactions, intense stellar radiation, or vertical atmospheric mixing are altering the expected molecular ratios. These discoveries have forced researchers to revisit models of exoplanetary chemistry and dynamics, particularly for irradiated gas giants. Another groundbreaking observation targeted the exoplanet WSP-121b, about 880 light-years from Earth in the constellation Puppis. This hot Jupiter has a dayside temperature above 2500 degrees Celsius and is known for its extreme vertical temperature gradient, hotter in the upper atmosphere than below, a phenomenon called a thermal inversion. Using JWST's MIRI and NIR spec, researchers in 2023 identified atmospheric constituents such as vanadium oxide and titanium oxide, compounds rarely found in planetary atmospheres because they condense out at cooler temperatures. This supports the theory that thermal inversions are driven by these high-opacity molecules absorbing stellar radiation at high altitudes. Even more bizarre was the discovery of silicate clouds, essentially clouds made of rock particles on hot Jupiters, like WASP-76b and WASP-17b. In the case of WASP-76b, located about 640 light-years away in Pisces, JWST confirmed earlier suspicions that the atmosphere contains iron vapor on the planet's day side. The extreme heat causes metals to vaporize, and strong winds likely redistribute them across the planet. Observations from JWST in 2023 showed evidence of exotic weather patterns, including possible metal rain as iron vapor condenses on the cooler night side of the tidally locked planet. Meanwhile, WASP-17b, a planet 1,300 light-years away with a puffed-up, low-density atmosphere, was found to have clouds rich in silicate particles, with sizes ranging from submicron to several microns across. Data from JWST indicated light scattering patterns consistent with these mineral clouds. This aligns with earlier hints from Hubble, but adds a crucial layer of precision. These observations imply that exoplanet cloud formation can involve entirely different chemical ingredients and processes from those on Earth. One of JWST's strengths lies in its ability to detect trace gases and probe deep into atmospheres using transmission spectroscopy. For example, the exoplanet HD 20945-8b, one of the first exoplanets ever discovered, was re-examined with JWST. Located 159 light-years away in Pegasus, HD 20945-8b showed intriguing differences compared to earlier Hubble results. While Hubble had detected sodium and water vapor, JWST's instruments revealed a more complex chemical profile, including methane depletion and enhanced levels of carbon monoxide. These unexpected findings again highlight chemical disequilibrium and suggest dynamic vertical mixing or previously unknown photochemical pathways. Some of JWST's findings are so strange that they have sparked fringe speculation, though without evidence of artificial origins. For instance, HD 18973-3b, another well-studied hot Jupiter located 64 light-years away in Vulpecula, exhibited atmospheric haze and scattering patterns that don't match existing models. The haze is so dense and variable that it could obscure molecular features, complicating efforts to determine its composition. While this is likely a natural phenomenon, such anomalies challenge the assumption that exoplanet atmospheres can be neatly categorized. The possibility, however remote, of technosignatures, which are traces of advanced civilizations, remains an underlying motivation in some corners of exoplanet research, though current data offers no credible support for such claims. JWST's ability to study smaller and cooler exoplanets is also beginning to bear fruit. The TRAPPIST-1 system, just 40 light-years away in Aquarius, consists of 7 Earth-sized planets orbiting an ultra-cool red dwarf. JWST began observing TRAPPIST-1b and TRAPPIST-1c in early 2023. So far, it has not found strong evidence of thick atmospheres on these planets, but it has ruled out hydrogen-dominated envelopes for the innermost worlds. More observations are ongoing to detect water vapor, carbon dioxide, and other biosignature gases, if they exist, in the atmospheres of the outer TRAPPIST-1 planets. These insights from JWST represent a dramatic leap beyond what was possible with earlier observatories. Previous missions like Hubble and Spitzer could detect a handful of gases in large exoplanets, often with low resolution and high uncertainty. JWST, by contrast, is capable of measuring dozens of atmospheric constituents with great sensitivity due to its broad infrared wavelength coverage and unparalleled stability in deep space at the second Lagrange point, or L2, about 1.5 million kilometers from Earth. The upshot is clear. JWST is not only confirming the diversity of exoplanets, but is also revealing patterns and anomalies that suggest our models are incomplete. And in doing so, it is challenging the very assumptions that have guided planetary science for decades. the terrifying possibility our models might be incomplete. In response to the possibility that our current understanding of the universe might be fundamentally flawed, scientists are scrambling for answers. Experts have proposed various alternatives and adjustments to existing physics. Some theories suggest stretching the timeline of the universe using older ideas like tired light, which imagines that redshift might come from photons losing energy over time rather than expansion. These models extend the age of the universe to about 26.7 billion years instead of 13.7 billion, giving more time for early galaxies to develop. However, these approaches struggle to match other precise observations, such as the uniformity of the cosmic microwave background and data from Type 1a supernovae. A more mainstream alternative involves modifying the role of dark energy. Research published in the European Physical Journal PLOS in August 2024 examined how dark energy might have evolved over time rather than remaining constant. Using the Chevalier-Pulaski-Linde, or CPL model, scientists showed that a higher concentration of dark energy in the early universe could have accelerated the formation of massive galaxies. This tweak could potentially explain why we see galaxy clusters at redshifts between 7.4 and 9.1 with masses in the range of 10 to the power of 10 to 11 solar masses. But again, this fix has its limits. It must align not just with JWST data, but also with past observations from the Hubble Space Telescope. And so far, it doesn't. Adding to the tension is the long-standing discrepancy known as the Hubble tension. Local measurements using Cepheid variables and Type 1a supernovae suggest the universe is expanding at about 73 kilometers per second per megaparsec, while global estimates based on cosmic microwave background data from the Planck mission indicate a slower rate of around 10 kilometers per second per megaparsec. A 2024 analysis by Ars Technica found that JWST's parallax measurements continue to support the higher local rate, deepening the divide. Even prominent cosmologists are starting to acknowledge these cracks. In June 2024, George Efstathiou, one of the key figures behind the Planck mission, co-authored a paper on RxIV outlining where the Lambda Cold Dark Matter model excels and where it stumbles. Alternative models, once fringe, are gaining traction. Modified Newtonian dynamics, or MOND, originally proposed by Mordechai Milgrom in 1998, argues that gravity behaves differently at very low accelerations, negating the need for cold dark matter. MOND offers a better fit for JWST's observation of early massive galaxies, but faces challenges in explaining phenomena on large cosmological scales. Perhaps the most comprehensive alternative is early dark energy, or EDE, which proposes a brief period of intense dark energy before the epoch of recombination. EDE might reconcile both JWST findings and the Hubble tension. Still, not everyone is ready to abandon the Lambda Cold Dark Matter model. For now, we can only wait and see how the future molds our understanding of the universe. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.